But I've got a good friend in Brighton who does a lot of modular work and builds his own modules. He's encouraged me to come and I really want to get into it as well. Not least, it saves. I will enjoy it, but it will save quite a bit of money actually.
Yeah.
If you do it that way. I mean, it's half. I don't know, or something like half the cost, isn't it? When it's built.
Yeah.
So yeah. So looking to really get into it. Looking forward to this.
So I'm Tom, and I design the Music Thing modules. About probably getting on for 10 years ago, I came to a workshop exactly like this in Brick Lane in London. It was held by Tom Buggs, who's a designer in Bristol who designs those kind of weird blue modulars. And he did a workshop, like I say, exactly like this, building a little sort of standalone sort of oscillator board. Before then, I'd really never soldered anything at all, let alone made any electronics. So I did that, realized that it's a bit like riding a bike. Once you've learned that basic skill, you can just do it and it becomes a thing you can do. It's straightforward. But like riding a bike, it's pretty much impossible when you first try and do it. So I can very clearly remember when I started out just going, how is this a thing that people can do? You know, you sort of poke this thing with a soldering iron, you get like weird blobs of metal come and it doesn't stick where you think it's going to go and it doesn't do what you expect it to do. So when you're starting out, don't be at all surprised if that's how you find it for the first bit. And then once you get the hang of it, it is pretty straightforward. And partly that is also about the equipment. So if you've got, like I said, if you're struggling, if you're trying to use lead-free solder, that can be quite tricky. If you've got a sort of weird knackered soldering iron, that can also be a problem. And things like keeping your tip clean while you're soldering it sort of feels like a little thing, but it's the difference between it being easy and straightforward and kind of enjoyable and just really frustrating and difficult. So if you're during this at that point where you're finding it frustrating and difficult, there are some experienced people around here. I can certainly help. Steve can help. I'm sure Will can help. There's a few, or any of the Wills can help, I'm sure. You know, the one of the reasons I was really keen to see Thonk doing these events is because it's much easier to do as a group than it is to sit there at home going, how do I make sense of this? And I remember when I first started doing kits as well, you look at it and think, what side do the components go on? And it seems like such a sort of basic thing. And once you know, it seems really stupid and obvious. But the first time you're doing it, you're going, well, it's not obvious. It's not immediately apparent. So by all means, if you have any questions at all, do just raise them. And I can guarantee I will have made the same mistakes as you, and I will have had that same situation not really that long ago. So kind of thank you very much for coming out to Brighton on a beautiful sunny afternoon and sitting in a room listening to me talking about graphic equalizers, which is what I'm going to do for a little bit now. So I think graphic equalizer is one of the things that is kind of it's probably the best known piece of electronic kind of sound modification that exists, because all through the 80s and the 90s, when looking around, most of us, I think, were growing up, you had these things all over the place. So every cheap sort of stereo you bought from Dixon's had this little graphic equalizer on it. And often the first experience that people would have of ever kind of changing a sound and tweaking a sound came from that experience of just fiddling with it and, you know, pumping the bass up and just, it was the first way that you were able to ever actually kind of interact with audio in that way, which is why we've got Ferris Bueller here if you've seen Ferris Bueller recently, it's an extraordinary music gear film. It's got like emulators and samplers and all this amazing stuff that he has in his bedroom. So at one end you've got Ferris Bueller, the other end you've got Stockhausen. I have a feeling this isn't technically speaking a graphic equalizer. I think it's a kind of fixed filter bank. But basically, if you've got Ferris and you've got Stockhausen, that's the kind of probably my spectrum of interest, really. And if it's somewhere between those, it's probably something interesting to look at. So I started trying to find out when I was starting to prepare the talk, I said, well, where do these things come from? What are they? This, as far as I can work out, is the first ever graphic equalizer that I think is, I couldn't quite get a grip on the date. I think it's probably 1930s, could be a little bit later. And it was built for cinema sound. And you imagine if it didn't exist, being able to just nudge up the voice a bit, nudge down the kind of rumble in the background would have been an amazing kind of revelation for people doing cinema sound at that stage. And you can see just how vast it is. So you have this enormous block here that's all, I guess, valves and inductors, which we're going to talk about in a bit. I assume there's one of these for each of the channels, and then this fantastic little remote control leading up to the kind of control panel, which is probably, as we'll come on to a bit, is probably switches rather than faders and kind of potentiometers like we have. So that seems to be the first one ever, and these were used in cinema sound, but weren't kind of super common. Then this thing came along. So this is a Langevin graphic equalizer. These were really, I think, pretty popular. This is, a relatively small unit. I would imagine this is transistors. This certainly wouldn't be valve. Actually, no, this doesn't have transistors because this is passive. So if you put this into the signal, the whole signal level kind of drops down, and you need to put an amplifier after it to sort of bring it back up. But this, you can see, was a pretty compact little unit, and there's one here. I don't know if you can see there, this is from the Motown engineering department. So Motown used a bunch of these in their studios, and this is considered by sort of people who study such things to be a big chunk of why Motown records sounded the way they did, and being able to just shape those kind of bass sounds and shape and just manipulate what you were doing much more easily. And what I really like about these overall is just it's a really lovely interface. So later in the 70s, I think, was when those parametric EQs were invented, where you could fine tune the exact frequency and the boost and the cut. And that was obviously much more precise and detailed. And when you have those enormous studio desks with every channel had like 4 or 5 of those in it. But I always think with graphic EQs, there is this just really simple, quick immediacy in the interface. So where have I got to here? In kind of modular synth land, you don't normally have much in the way of traditional kind of EQs where you boost and cut. You normally have filters for everything. So obviously a filter can do a lot in terms of cutting high frequencies if it's low pass, cutting low if it's high pass. But it's quite a different sort of experience to that experience that we had growing up fiddling with the EQ on your stereo. And I did in the past I did a module which was a simple kind of 2-band EQ. And again, it's just a nice thing to have in your modular, just being able to tweak the overall sound a little bit rather than that very precise kind of voltage controlled filtering. So old Moog modulars had fixed filter banks like this in them. So this is one of those things that is considered this kind of amazing, makes things sound fantastic. I've only ever sort of used one very briefly once, and it did seem to immediately make things sound fantastic. And you would put, you run an oscillator through it, and it's got, you can see the bands are actually quite closely spaced. So it's not like a graphic EQ that has the whole frequency range. This has like 250 to 2.5K. So it's really shaping the sound of maybe an oscillator rather than you run the whole mix through it and get that kind of graphic EQ effect. So I was kind of interested in this as a thing that, again, maybe that would be a useful thing to have in a modular. One of the reasons these have such kind of status and they're very expensive and rare is because they are made with inductors. So these things are inductors, and they're basically big coils of wire. And we have a proper electrical engineer here who will be able to correct me if I'm wrong on these things, which I often are. But essentially, in the olden days, up to about the 1970s, if you wanted to do EQ in this kind of way, you'd probably use a bunch of capacitors and a bunch of inductors. And inductors now are very, very hard to come by because, as we'll see, they've been basically replaced. So if you said, oh, I want, 6 or 8 bands of inductors of different sizes, it would cost you a fortune, and you'd have to get them probably hand wound to your requirements. Presumably when he was doing this, they were a bit easy to get hold of, but you can see they're big, and these would be the bass channels. They're big, chunky things that you wouldn't want to try and put behind a Eurorack panel. So fortunately, in 1948, he's probably Dr. Tellegen, invented a thing called a gyrator. And I didn't know this at all. I'd kind of vaguely heard about this. But before silicon and semiconductors and like microchips and transistors were invented in the sort of 50s, if you were doing electronics, basically you had 4 elements. You had resistors, it's their capacitors, inductors, which are those little coils, and transformers, which are basically big coils. And that was pretty much what you had to play with. Those were considered the 4 elements that you used to make electronics up, the passive elements. So you had valves and things where they were active. Dr. Tellegen discovered a thing called a gyrator, which was the 5th element of electronics. It was a very big deal when it happened. As you can probably tell from talking about it, I don't really understand the details of how a gyrator works. But what it meant was you were suddenly able to do the kind of things you did with inductors using a couple of little components like resistors and maybe you'd much smaller, simpler circuits. So that meant, then the second invention. So you had Mr. Tellegen inventing the inductor. Then you had this guy, Bob Woldar, who was working for Fairchild in the 1950s, I think, probably 1950s. And they were essentially an arms company, and he was part of the team that was designing guidance systems for rockets. And in the sort of 40s, 50s, probably into the 60s, analog computers of the kind that we're using here became really interesting. People were really interested in them because they were for exactly those kind of guidance systems in rockets. In World War II, he worked on fire control systems for like guns and artillery banks and that kind of thing. And he then invented the op-amp. An op-amp is, you're going to see a lot of them when you're making this. It's a really basic building block that's used in any module here, in any amplifier. And you can do the sort of things you do with transistors, but essentially an op-amp contains dozens of transistors in a silicon chip, essentially. So he invented that. So you've got Mr. Tellegen, who invented the gyrator, Mr. Waldar, who invented the op-amp, and that then means you're able to make really cheap, simple, easy graphic equalizers and other types of EQ. So I think I had one of these Walkman in the 80s, I guess, and you can see just how simple it was for them to put a couple of faders. I think there's a couple of either transistors or little op amps there, a few resistors and capacitors, and they were able to make something like this, mass produce it, sell it very cheaply. So that whole sort of journey from those enormous tube lumps in the 1930s to something that literally can run off a battery very, very cheaply in the 80s. And the other thing made in the 80s was this. So this is a really, really common, popular Boss guitar pedal. So when they're designing a pedal like this has exactly a circuit that's very similar to the circuit that we're going to build here. But it has to work off batteries, and it has to be cheap because that's what they need, and it has to be built in the 80s because that's when it was designed. So in the 80s, if you wanted to make something cheap and run off batteries, you had to use kind of low power op amps or low quality kind of cheap op amps essentially, and you couldn't use much power, so you don't want to draw much from the battery. And when you're designing a circuit, essentially, if you don't want to draw much power, you use big resistors. This is a very crude way of doing it. And big resistors cause noise. So if you've got one of these, they're great, but you plug it into a guitar amp, as soon as you turn it on, it goes shh, and creates a lot of noise and hiss. And you can buy them. I mean, I've got one where you switch out the op amps for slightly more modern ones, and then it's a little bit quieter. But basically, it works really nicely, but is kind of noisy and irritating. So I was looking. I think somebody on Muff Wiggler said somebody should make one of these in a module, and I'd been thinking, well, I've already been kind of wondering about that. Started looking into it and said, okay, I would like to make essentially one of these. I think it'd be useful and interesting to have. I then, at some point, had the idea of putting the faders diagonally, and then suddenly thought, okay, you could actually make this small enough so it's kind of a nice thing to have. So found this circuit, and this is literally a textbook circuit. If you get into this stuff, buy this man's book, because it is really fantastic. It's really the only electronics textbook I've properly read and probably been through all of it, because it's really clear, really simple, easy to understand, and it's got diagrams like this in it, which you can literally pick up, put into a module, and it works beautifully. So the way this, I'm not going to go through this in too much detail. Essentially, when you're looking at this, these are the faders. So you've got 7 of them running across there. The signal comes in here, and then each of these is that gyrator I was talking about. So each of these, the capacitors there, the resistors there, and the resistor there are all different, but otherwise the circuit's exactly the same. And the resistors and the capacitors set the exact frequency that it's tuned to. So if they were all identical, you'd have 7 faders that would all move like 1 kilohertz up and down, which would not be terribly useful. And that's essentially what the circuit does. One thing that you'll notice when it comes to sort of demo it later on, these little arrow things here underneath it show the phase of the signal, which I'll talk about more later. But essentially, this whole circuit flips the phase of the signal upside down, which is quite important when I'm demoing it later on. So I take that and you put it into a software program called Eagle, which I use for designing circuits, which is this really peculiar program that has been around, I think, for sort of 10 or 15 years. And most computer programs, you can come pick it up and you can sort of understand how it works. If you use Photoshop, you can use Illustrator, and use Word, you can use most word processors. This is just completely different and weird. When you first start trying to use it, it is completely incomprehensible. It does everything in a weird, difficult way. And if you spend long enough to learn how to do it, as I have, you develop complete Stockholm syndrome, and I would never shift to anything else, because now I've learned it. All that sunk knowledge and learning how to do it means I'm kind of stuck with it. So this is the circuit, and I'll just very briefly kind of explain roughly what's going on here, because this will look, one of the things I've found really sort of satisfying about the journey learning how to do this stuff is, to me, I can look at this and I go, oh, I understand what that does. And I can remember when I first started looking at things and just thought, this is completely incomprehensible. This is quite nice because it is it's a very repetitive circuit, so it's relatively easy to explain. So here is where the power comes in. So that's got the sort of 10 pins that you'll be familiar from Eurorack modules. Power comes in there. That there is a pair of diodes that just make sure you don't connect it the wrong way around. So if you connect the power the wrong way around, it won't blow anything up. And then there are a couple of big capacitors there, and they basically act like little batteries. So they charge up when power connects in. And then if the module needs more power, like in a fraction of a microsecond, the power can come out of that, and it makes the power more stable, essentially. Because if you've got a big bass sound coming through a module, it's having to push the voltage kind of up and down like that. And that can draw a little bit of more current than it would normally. And if I'm saying this wrong, you should definitely stop me, but that's essentially the kind of how I understand it. So that's why you have a couple of big capacitors there. So then the power runs down these lines here and off into, and these are the op amp chip. So each of these has 2 op amps in it. So there are, what is it, 2, 3, 4, 5. There's 10 op amps there. And just see if I can, there we go. And then these are sort of banks of resistors and capacitors that do the tuning of the frequency of the gain. So, and then down here, on the sliders we're using all have LEDs on them. And so this provides the power to all those LEDs on that side. So that's basically how it works. So when you open it and look at it, you can kind of see what's going on a bit, hopefully. And I think that is basically it. That's how it came to be. That's kind of how it works. So we should probably now get started. Who wants to practice on something else before they practice on the main kit?
Well, yeah.
Let's all show them out. What have we got, Steve, to put out?
Yes, I think there's not one set
We're
up that
We can do a test with some jacks on these
Okay.
PCBs and resist. There's no resistors in the graphical Q kit to solder, but they're a good practice.
So there's some in here, or just to solder them in?
Bag of jacks. Yeah.
Okay.
What PCBs are
They're all PCBs.
Okay.
they? They do have resistors.
They don't. Okay. So let's just spread these out. Why don't you take one and pass one on, and then if we take like, just take one board, yeah, and then take some resistors so you got them on the side anyway, and then take maybe 3 or 4. Just take 3 of those. And then we need to turn these all on, don't we?
I don't know how many. I just take 3. Are these all the same value resistors?
I don't think, yes, they are. I'm not sure we're going to, do these actually work, these boards? No, we don't, because we don't have any, that's fine. No, let's just do this. Let's just do the soldering, yeah. So,
I've never been able to remember, no matter how much of the electricity resistance.
I've always just measured them if I need to know. And got kits from Thonk where they're labeled.
Very good. Thank you, James.
Best.
You take 2 or 3, yeah, so we can just put them in.
Giving it to you on
Right, so I've never made one of these, so I'm looking to the Thonk people for. So if you look at the PCB, you'll see one side has got silkscreen, the white on it. They've both got silkscreen on it. One's got silkscreen kind of squares around all the sockets at the bottom. Can you see that? And the other side has got a big Thonk logo. So the way this would work is the sockets will go on the side with the squares around them. And you can see there's, for each socket, if you start at the bottom, there's one hole at the bottom and then 2 at the top. And the socket is the same setup. So they go in just like that. Everyone got that right?
Yeah.
Perfect. So it's that way around. Yeah. And then you go the single one at the bottom. That's right.
Like that, yeah?
Like this. So see that whole, hang on, use that as a pointer. So that leg goes in there.
Right.
That
So you
leg
got the-
goes in
I see, 'cause
there.
it's bent out.
And then that bends out. Yeah,
Right,
sorry.
so
That's,
you've got to just so
you squish it in like that. Yeah.
There's 2.
R1 again.
R1 is and R2 and R3.
So it goes from left to right.
Resistors go in anywhere.
So it doesn't matter if you're on a laptop, you can solve it that many times.
So we got some solder. Are you? Brilliant.
For this particular one, they're actually all the same.
If you run out of solder, we've got lots more.
So it's more like, so you can say, sometimes you can have a bit of paper and it'd be like R1 is that value, R2 is that value. It's more just a reference.
Here's my
So you can say that's, yeah.
So then the trick with soldering, I was saying very confidently, working out how to explain what the trick with soldering is. The way I do it is first of all, you want to make sure the end of your soldering iron is shiny and clean. So let me get a bit of solder here. So that's brass shavings, and you just dab it into that to clean it off. Now let's see how this is working. So then before you worry about the board, just get your soldering iron, dab it off so it should look nice and clean, and then just melt a bit of solder onto the end. You should get a nice little dab of smoke. And if you breathe in a lot of it, you get a headache, but it's not.
The fumes don't contain lead.
No.
The fumes contain the flux, which is a chemical inside that helps the lead to melt and tip. But yeah, it's best to not breathe in at that moment.
No. So just dab some on the end, and you should see it melting smoothly. That's right. Yeah. And then once you've done that, just dab off to clean off that solder, and you should have a pretty nice shiny silvery tip.
And then that's ready to.
So then what you do is, and it's harder to do where you can't all see it, but it's essentially the principle is you hold the soldering iron to the pin. The pin gets hot, then you touch the solder to the pin. What you often have to do is get a little dab of solder on the tip, because that helps transfer the heat across. So
how long does it take for that pin to be hot enough?
Well, let's see. If I just do it now, I'll do touch, and then that goes on nicely. So 2 or 3 seconds probably. If you're holding it on for more than about 10 seconds, it might all get really hot. If you're just dabbing it for like a second, it'll be quite hard.
The other thing that's a good habit to get into as well is you touch the solder to the very thinnest tip of the iron, it's actually the coolest part. It's a lot hotter where it's thicker. So
that's a good point, yeah.
Touch the solder higher up and then move down, you get a nice kind of flow of solder, and you get a capillary action where it sucks into the hole.
So that's the thing, yeah, the capillary action is really important. When you're doing, once you've sort of melted a couple, have a look, and you should see that when you melt it, it literally sucks down into the hole, and that's when it's done right.
Be mindful of that.
Safety goggles on the table.
So
sometimes solder can.
I would try, see if you can do it just holding it, just keeping it on the table like that, because it will singe your finger as well, possibly.
Get the soldering iron right into the circle. So you're touching both parts, yeah. And then introduce the solder.
So I would put the iron on the far side there, and then you can poke the solder in. What you're not doing is transferring the solder off. Don't try and transfer the solder off the iron.
No. So
you just do it like this. So you heat it like that.
You don't with these.
Then you just touch it and it sucks in.
Oh, I was putting the solder on the iron.
No, you can't transport it across on the iron.
With you.
Because it needs the flux that's in there once it's melted. Just that, yeah.
One thing I'd recommend is you try and with the hand.
So there you have transferred it across, and that's fine. Clean your tip and just try the one underneath. So
Heat it up.
yeah, put it. I put it behind like that.
Yeah, just behind the thing.
Yeah, and then that's right, and then poke it in. There you go. That's pretty good. And then sometimes it sticks on, so just heat it up again, and then it'll melt off.
takes a little bit of time.
Again, if you put it around the back,
Yeah.
there you go.
That's it. Okay,
That's a
right.
pretty good joint. that
Okay,
one.
yeah. Oh, I see then, right. It's a lot, obviously, about technique, isn't it?
It's pure, and
You
like I
could
said,
actually see how you could get really good at it.
it is literally riding a
Oh,
bike.
I
Once
see,
you've done
yeah.
it a bit, let me
But what
put
you've got to
another.
be really careful of, isn't it? Because once you've got into the situation, say for instance, like there,
Yeah.
where there is a hole directly behind it, but that's obviously
If you-
follow components.
Yeah, if you got that in there, yeah, because that
you'll
goes
end up
here.
bridging it if you're not
Yeah,
really
so you do have to be careful.
Just done just that.
Let's have a look.
Be really careful on there. I see. Okay. That,
I think that's probably fine because the other thing that you can't quite see is the green, the solder mask, is it won't stick to the green, the solder. So when you do,
that one's all right.
yeah, that one there. I think it may be, and that is very close on the board. I suspect that's fine actually.
These two here, are these going to be one block or separate?
It wouldn't matter if they were.
Is that just pulled it?
Yeah, so when you the solder mask is magic, particularly when you do a surface mount stuff, it's incredible. You can just basically spread solder across it, and it all goes into the right points. So yeah, if you've got
So SMV isn't as difficult and fiddly as it's made up.
it's very, very fiddly, but it's different. So yeah, if you've got one that's a funny shape, you just re-melt it,
Yeah.
and it should suck into place. But those both look
Be
fine.
careful getting cheap ones because the
Yeah.
low wattage causes you a lot of problems.
Yeah, we'll just do that now.
Yeah, and if you've got a board where there's a lot of metal basically.
Anyone need any help? How are you doing?
I think
Yeah, it's just they're not I'm trying to make them look alike.
They look fine. I would say that, I mean, there's slightly more solder than you need, but they look fine. And it's making sure, I think it probably is, but make sure that has
The first one that I did,
sucked down.
that was the first one.
Can you just reheat it and see what happens? See if it sucks a bit more into it. You can leave it on for a bit longer than that. There you go, that's right. Yeah, so you see now it's, I think a bit more has gone inside and it's more that sort of shape.
Mm-hmm.
You don't want it to be that sort of shape. You don't want it to be a blob on the end. Because if you look, imagine the hole there, that hole is lined with tin all the way down. So you want